Hello again, everybody. Test one should be behind us now. So it's time to move into our second section of the course. In our second section here, we're going to continue with probability and probability distributions. We're going to transition now from week 5, where we talked about discrete probability distributions and focused on the binomial distribution, to this week where we're going to focus on continuous probability distributions, and the normal distribution is the most common one of those. So starting out with just continuous distributions in general. Key concept, the standard normal distribution is going to be one of the big ones. Remember, the normal distribution was that bell curve. The standard normal distribution means that the mean is 0, so the center of that curve is at 0, and the standard deviation is 1. So we go out steps of 1 in each direction. If you remember the empirical rule, so this would be -1 to +1. The empirical rule tells us that from 1 standard deviation below to 1 standard deviation above, that's 68% approximately of our data. And to 2 below and 2 above, that was 95%, and continuing on with that. That empirical rule actually comes from standard normal probabilities, and we'll be able to get exact numbers a couple more decimal places, so slightly off from those numbers given as the approximate empirical rule. The actual formula for the normal probabilities and normal distribution looks like this. It's kind of an ugly formula. E is a natural constant. It's the ln of E is 1. It describes exponential decay and charging and capacitors and continuous compounding interest rates and stuff like that. It's just one of those constants like pi. Actually, we have pi in this formula too, that is just a set number that gets used over and over again in different applications. X is the value that we're trying to find the probability of. Mu is the mean. For normal, standard normal, is going to be 0. And sigma here is our standard deviation. For standard normal, that equals 1. And of course, this sigma also is the standard deviation of 1. That formula is ugly and it's hard to use, so we're going to look at other versions, other methods of calculating it. We're not going to use that formula for any of our calculations here. We're going to look at the curve and calculating the curve. Now, some things to remember the curve about our standard normal curve is it is symmetrical. It's the same on both sides. So that means 0 here, half the probability goes to the left and half to the right. The total, since this is a probability distribution, the total probability has to add up to 1. So the area under this has to be a total of 1, meaning we have 0.5 on the left of the center and 0.5 on the right of the center because it's symmetrical. So that helps us estimate some of our probabilities, or at least check the reasonableness of some of our probabilities as we go on. Before we get any further into the normal distribution and the standard normal distribution, let's look at something called the uniform distribution. The uniform distribution is another continuous distribution. So it's rectangular, and just like any other probability distribution or density function, total area has to be 1 because the total probability has to be 1. The uniform distribution is going to take the shape of a rectangle on our graph. And so we know the area of a rectangle is height times width, or width times length times width. Let's take a peek at some examples of this. So for that uniform distribution, it is a uniform continuous random variable. It's uniformly distributed if the chances are equally spread out along the whole range of the possible values of the variable. And you've heard me, I mentioned this word earlier. A density curve then is the graph of a continuous probability function. The probability is the area contained underneath that curve between the values that we are looking at. So an example, this will be of a continuous distribution, waiting times at the airport. So at JFK Airport, wait times at the security checkpoint are between 0 and 5 minutes. So that's illustrated by this graph here. The bottom down here shows you the range and wait times. It goes from 0 to 5. Now remember that total area has to be 1, so we can find the height of this as area equals length times width. Well, the area has to be 1, the length of it is 5, so the width has to be 0.2 to make that multiply up. So that height there of 0.2 could be thought of as the total area of 1 divided by the range down here of 5 gives us that 0.2. We see that being a continuous distribution, any value now between 0 and 5 minutes is possible. So it could be 1.2 minutes, it could be 1.23 minutes, 1.2, 4, 5, 6, 7 minutes. That's the nature of a continuous distribution, is we can go to as many decimal places as we want to within the range. Every value in that range is possible. It's not just certain values along the range anymore. So if I want to know, the height of 0.2, I already showed you where that came from because the total area has to equal 1. So 1 divided by that range of 5 gave us the 0.2 for the height. Come on. So let's say we want to look at finding the probability that a given passenger, a randomly selected passenger, has a wait time of at least 2 minutes. So here's 2 minutes right here. Now, one thing about continuous distributions, any continuous distribution, is since there's an infinite number of possible values, the probability of equaling a certain value is always 0. Because if it was more than 0, an infinite number of those would add up to something bigger than 1, and we can't have a total bigger than 1. So what we need is to look at ranges. That's why we said at least 2 minutes. It means we're going from 2 up to, well, it can't go bigger than 5. So at least 2 minutes is really saying between 2 and 5 minutes. So remember, the whole area is 1. We're just looking at the area from 2 to 5 now. So we're looking at finding the area of that rectangle. And there we find it. It is 3 units long and 0.2 units tall. 0.2 times 3 gives us 0.6 probability. So the probability of being greater than 2 minutes wait, or between 2 and 5 minutes, it'd be the same in this case, is 0.6. So now back to the normal distribution, and I'm not sure why my marking is stacking up on us there, but so there, I paused for a second and reopened it so that we didn't have to deal with the inking sticking around. We're looking now at the standard normal distribution is the one that's really the most useful. The big thing, again, is the mean is 0. So the center of this is at 0. And the standard deviation is 1. So it goes out in steps of 1 in each direction. Standard normal distribution represents z-scores. So as we're looking at this, we're standardizing every population so it can fit into the same data distribution. Part of the reason for this is table A2 in your book. That is page 778 if you have the physical copy of the textbook. Otherwise, it's just table A2 or in the appendix if you're looking up in the ebook. That table only lists z-scores. And as we're looking at it, you'll see negative z-scores on the left-hand table at 778, positive z-scores on the right side table of 779. And we'll look more at how that table works as we go through examples. So it is designed to only work for the standard normal distribution, which means we have to have the mean of 0 and standard deviation of 1. And we can convert any data set, any set of numbers into that by using those z-scores. So that's why we do the z-scores. The probability that the table is showing us and the probability we're going to get from Excel when we look at examples of that is for a given z-score. So this would be a negative z-score because remember the center is 0. 0 would be right here. What the table or the Excel is going to give us is the probability of being less than or to the left. So if this is my z value, this over here is the probability of Z being less than whatever that value is. I'll call that value A for right now. So it's a cumulative area to the left of the boundary located at that particular Z value. When we're working with the bell curve, it's important to keep straight the difference between Z-scores and areas, because Z-scores tend to be close to zero. It can be often easy to confuse them with probabilities. Remember, the probability is always going to be between 0 and 1. Z-scores will be typically between -3 and +3. They could be outside that for really extreme values. But you can see they're going to be really close in value to a lot of our probabilities. So when we look at our bell curve, the Z-scores are the values that go along the bottom here. The probability for this Z-score is this area under the curve to the left of that Z-score. This is the way Excel calculates all these probabilities, and the table in your book calculates these probabilities. For the given Z-score that you look up, the number that's given is the probability of being to the left of that value. If you are using the TI-83 or 84 calculator, that calculator actually asks you to put in a range of values. Has some definite advantages for a lot of probabilities, but it also has some disadvantages that you have to work around trying to find certain probabilities as well. So look at this question here. In this example, we're going to do the bone mineral density test. It shows the likely susceptibility to different bone disorders like osteoporosis and osteoporina. It is often measured as a Z-score, with 0 being the mean. The average person has a bone density that would give us a bone density score of 0 and the standard deviation of 1. So it would look something like this. So if we want to ask the question, a randomly adult undergoes a bone density test and gets a score, what is the probability their score will be less than 1.27? So 0, remember, is in the middle, so a positive 1.27 is over here. Probability of being less than is this area here. If we use Excel to find that, the command in Excel is equals norm.dist. And I'll select that function right here. Now, I have the little hints that pop up so I know what to enter, but if you don't have that popping up, you can just click on the f of x here. They'll bring up the window. My x value is 1.27, mean of 0, and standard deviation of 1, and cumulative is always going to be true when we are using the norm.dist function. Remember, binomial distribution, false meant we were looking for a single value, true meant we were looking for less than or equal to that value. Well, for a normal distribution, being exactly equal to a value, it doesn't make any sense. We're always looking for a range, so the cumulative will always be true. We get 0.89796 is that probability. They round it to 0.8980. If we were using the table in the appendix, what we would look up, and this would be on page 779, because the positive values, what we would look up on the right side is 1.2. So the first 2 digits of that are on the left side of the table. And on top, we would find 0.07. That's the third digit of that. And we'd find where they cross, and we see that that is 0.8980. So this is just the rounded value from what we got with Excel. Because what the table gives us and what Excel gives us is the probability of being less than, or the area to the left, what we get from the table or from Excel is the probability we're looking for. It is that area less than our Z-score that we gave. So, as we said, we were going to find that area. Excel command is the normal dist. If you're not going to use the function command, you can just type in 1.27 is the value we're testing. 0 is our mean. 1 is our standard deviation. And then for true, you can put in 1 for true, 0 for false, or you can type in the words true we want true or 1 always for that function. So if you want to take a shortcut, you could just put 1 in there to indicate true to shorten up your time. And here's again how we entered. Notice entering 1 there shows us true to pop up. When we did it, we entered the word true, and it gave us the same thing, it's true to pop up. So it's this shorter way of entering true is all that is. Either way, the probability of having a bone density score of less than 1.27 is 0.8980. And there's the summary of that result. What if we wanted to find out what's the probability someone will have a bone density of greater than -1? So the probability that Z is greater than -1, and we could say greater than -1.0 or greater than or equal to means the same thing for a cumulative or for a continuous distribution, because the probability of being equal is 0, so it doesn't change anything. So it's the same as saying the probability that Z is greater than -1.00. We're using Z in there because we are testing Z scores. Once we get to the generalized formula, it's going to be X that would go in there rather than a Z. So if I want the probability is going to be greater than a -1.00, that would be right here on the bell curve. What the table or Excel is going to give us is this area to the left. So we would look up page 778, the left-hand side. We'd look up -1.0 here, and then 0.00, oops, on top of the page as well. And as we go down there, we find that that corresponds to 0.1587. Or we could use Excel. And Excel equals norm dist from -1, mean of 0, standard deviation of 1, and then 1 for true, for cumulative. Again, 0.15866 or 0.1587. But we want the probability of being greater. So the table and Excel are giving us the probability of being less. To get the probability of being greater, we use the complement. We do 1 minus the 0.1587 to get 0.8413. The probability that a randomly selected person has a bone density test score of greater than -1 is 0.8413. So to summarize that result, right here, that probability is 0.8413 that someone is going to have, any randomly selected person will test above a -1 for their bone density test. So now let's look at being between two values. Now this is what the calculator does well. I'm going to go back and look at some of the stuff on the calculator. Let's step back here and do this example. For this one on the calculator does the normal probability. It does a range with the normal distribution function. It actually uses normal CDF. And what it does is it goes from a lower limit to an upper limit with a mean and the standard deviation. We don't need a true or false for cumulative because, well, this is going with a range rather than less than or greater than. To be greater than -1, obviously the lower limit will be the -1. The upper limit would be positive infinity. And the way we enter infinity, there's a couple of different ways we enter infinity in the calculator. The easiest way to do that is 999999, 6 nines in a row. So on the calculator, it'd be second distribution, to go to the distributions. Option 2 is normal CDF from -1 to a positive infinity. I don't need to put a plus in front of it, it's just infinity. So 6 nines with a mean of 0 and standard deviation of 1. and I get that same probability, 0.8413. So now as I move down to this next one, finding the probability that a randomly selected person will be between -1 and -2.5, the calculator is custom built for this. Second distribution, normal CDF. Now the lower limit is actually the -2.5, that's the smaller number, to a -1 with a mean of 0 and standard deviation of 1, and it's going to spit out that probability, 0.1524. Let's go through doing it with Excel or with the table in the book. To find the probability being between, since the table and Excel only give us the probability of being less, this probability of being between -2.5 and -1 can be broken down into two pieces. The probability that's less than -1 and the probability that's less than -2.5. And if we take this little piece and subtract it off, what we have left is the desired area. So we can either look up in the textbook, in the table, the -1.00. Again, that's -1.0 and then 0.00 on top, which gave us the 0.1587. And then for the -2.5, it'd be -2.5 on top, 0.00 again. And that would give us a 0.0062. And we would subtract those. The difference is going to be 0.1525. Or we could use Excel. In Excel, we would have to use two functions, equals normal distribution. We're going to start out with the -1, which is just what we had calculated before, and do the -2.5, and then subtract those, equals this minus this, to give us the 1.25 or 1.525. So both methods give us the same result of 0.1525 is the probability that a randomly selected person will have a bone density test between -2.5 and -1, which it puts them in that osteopenia category. And so the area corresponding region between two z-scores is found by doing that subtraction. You find the probability of being less than both of the values and subtract them to get the area between those values to get that probability. Some notation, we see a little bit of this. So the probability of being between A and B would look like that. Probability that A is less than Z is less than B. We could put equals in there. It would be the same probability, but we choose to leave them out just to save ink, basically. Probability of being greater than a value A is P of Z greater than A. That's where we have to do 1 minus the probability that Z is less than A. Of course, up here, this is the probability that Z is less than B minus the probability that Z is less than A to get between. And this one is just probability that Z is less than A because that's what our Excel and our textbook table give us, is that probability of being less than the requested z-score. Some little hints, make sure, sketch out the drawings like we did here. This one helps to figure things out, even this one. So it helps you understand, remember, the table and Excel are always giving you the probability to the left, so you know if you have to look up that just that probability, or do you have to do the complement and subtract it from 1. Those little sketches go a long way to help understand what's going on. And as we go to the next step, where we're trying to find the z-score that corresponds to a given probability, the same type of thing holds true. We're going to be doing an inverse normal function, or we're going to be reading the table backwards, which means in the table, we're going to be looking for a probability in the table and then reading what are the z-scores and the margins that correspond to that probability. So for the standard normal distribution, one of the things we look for is a critical value of z. That is, remember on our bell curve, that could be a value that's separated as significantly low value for our variable, so a really small probability of being smaller than that value, or a significantly high value for the variable, so a very small probability of being greater than that number. Z sub alpha represents the z-score where the area is alpha to its right. So if this area here is alpha, this would be z sub alpha, is that z-score that corresponds to that probability. Notice that's backwards from the probability given to us by Excel and table A2. So we're going to have to use complements when we're dealing with that. So find alpha of 0.25, find z that goes along with that. So we're looking at our bell curve here. This is the z-score we're looking for. This area here is 0.025. So since our table and the table and Excel give us the area on the left, not the right, we have to do 1 minus 0.025, which gives us 0.975 as that probability. That's the one we're going to be looking for. And it shows us that calculation here of what we're going to look up. So really small values, again, would be up on this tail or this tail. Remember we said 5% or 0.05 is what we often use. Since it's symmetrical, that often gets split half to each side. So that's where that 2.5% or 0.025 came from and why we're looking it up here. So what we want to find is the z-score that corresponds to the probability being to the left of 0.975, like I showed here in this table. So to do that, we can either use Excel using a normal inverse, or we can use the table backwards. If I'm looking in the table, I'm going to look in the body of the table. Now, since this probability is greater than 0.5, that tells us we're in the positive z-scores. So we're in the table on page 779. We're looking for a number as close to 0.9750 as possible. And as we find that in the table, it takes a while to find these usually. I have a 0.9564 and a 0.95, oops, that's not what I'm looking for, 0.9750 exactly. I look above it, it's 0.06 and 1.9. So it's 1.9 over here and 0.06 up above, which gives me 1.96 is the z-score corresponding to that. Or if I used Excel, inverse normal. So norm inverse. Oops. Open up my function here. The probability I'm looking for is 0.975. Mean is 0, standard deviation of 1 again. And there you get the 1.95996, or rounded to 2 digits of 1.96. If I want to find z of 0.1, that's finding the probability. So z of 0.1 is this area here is 0.1, which means the area on this side would be 0.9. So that would be what we would have to look up to find that probability. And let's do it. Equals norm inverse 0.9. 0.1, we get 1.28155.